Good evening, good morning, good night, good afternoon. No, I'm not. Can you hear me?
Yes.
Yeah, okay, great. A good day to everybody from all over the world. I'm really sorry about the technical problems last week that we could not have this talk on. So Critical Transition Complex System Seminar Series is being jointly hosted by IIT Madras and Potsdam Institute for Climate Impact Research, Germany. This seminar series brings together experts from fields such as climate science, combustion, neuroscience, fluid mechanics, etc., and aims to disseminate the state of the art in the prediction of critical transitions in these diverse fields of study. The seminar takes place every month on the last Monday of every month. Today is an exception because we had to cancel last week. Before I introduce the speaker, a few housekeeping notes. I request everyone to turn off their microphones and please use Q&A box in the Zoom to ask the speaker your questions, and we'll have ample time at the end to discuss your questions and clarifications. Now, let me introduce the speaker for today. Professor Ginestra Bianconi is a professor of applied mathematics at the Queen Mary University of London and an Alan Turing Fellow at the Alan Turing Institute. She is the chief editor of Journal of Physics Complexity, editor of PLOS1 and Scientific Reports, and she is the associate editor of Chaos, Solitons, and Fractals. Her research on statistical mechanics and network science includes network theory and its interdisciplinary applications, and she has written a number of breakthrough papers. Today, Professor Bianconi will speak about the dynamics of higher order networks. All yours. Yeah, you can proceed to share the screen.
Yes, thank you so much for the invitation. Let me share the screen. So it's a real pleasure to be with you today. And I would like to discuss some work that we have been doing since the pandemic, I would say, on higher order networks and dynamics. So network science has been very successful in capturing the complexity of systems in interdisciplinary application using this very simple yet powerful tool of a network, which is formed by nodes and links. However, network can have limitation, and these are addressed, for instance, by higher order network. In fact, higher order networks are able to capture interaction occurring between two or more nodes, which cannot be accounted for in a simple pairwise network. And we have different types of higher order networks, such as a hypergraph, a simplicial complex, which is a structure which is amenable to topological analysis. And we have also network with triadic interaction, and I will discuss about that next. So in order to motivate, of course, many body interaction, higher order interaction can occur in a large variety of systems. And here I take just as a paradigmatic example, the brain, where you can have three regions of the brain that are correlated pairwise, leading to three pairwise correlated signals, or they can be activated at the same time in a three-way interaction, and this is typically described by a field triangle. And another set of higher order interaction occurring in the brain is, for instance, when you have two neurons interacting with each other and sending neurotransmitter to each other. But then you can have a third node, for instance, a glia, which can interact by absorbing some of this neurotransmitter. So it modulates the interaction between the other two nodes. So you have two nodes and a third node modulating their interaction. This is what we call triadic interaction. And these are three examples, a triangle or a triadic interaction that can occur on higher order networks. So why I'm very interested in higher order networks, because one of the central topics of network science is the relation between the structure of the network and the dynamics. And there's been a lot of research in this direction. But most of the research point out the role of combinatorial and statistical property in shaping the property of the phase diagram of higher order dynamics. Things, for instance, of percolation, which is shaped by the degree distribution, or epidemic spreading, also shaped by the broad degree distribution. However, with higher order networks, there are not only combinatorial and statistical property that play the role of shaping the interplay between structure and dynamics, but also simplicial topology and geometry. And these simplicial topology and geometry are characteristic of the structure of higher order network, which affected the spectrum of this higher order network and in the dynamics defined on top of them. So I have a research book, which is an introduction to these simplicial complexes, which has the goal to introduce to this question about how network topology and geometry shape network dynamics. And if you want to have a less personal account, but more synthetic account of this research direction, this is a perspective paper which I wrote with a number of distinguished colleagues, in which we show that actually in higher order networks, as we will discuss in this talk, dynamics can be really defined not only on the nodes, but also, for instance, on the links, and projected into triangle or node. And so you have really that your simplicial complex is fully alive with the dynamics not only defined on the nodes, but also on the links, on the triangle, on the tetrahedra, and so on. And this allows us to use and adopt topological tools to treat these dynamics. Before we go into the dynamics, let me tell you that in my group we had, in previous year, we had focused a lot also on structure and how to model higher order network structure and network topology and geometry. And this is an important research question, because in many contexts, you have the formation of network that actually define a clear geometry, for instance, the manifold of brain fiber in the brain or fungi network. And one question we have focused on is whether this network geometry that we observe is due to the network embedding, or is actually is an emergent phenomenon, actually to some combinatoric rule that do not make use of this network embedding. And this is a kind of a mathematical conceptual problem that is actually the problem of emergent geometry. So you have a rule that are purely combinatorical and statistical, and yet when you iterate this rule, you generate network with emergent geometry. And this is a problem that is dear to the people doing fundamental physics. And this is a very beautiful sentence by Roger and Perron saying that actually, in my own view, ultimately physical law should find their most natural expression in terms of essentially combinatorial principle. And so space-time should have a combinatorial nature. And so this question of how simple combinatorial rule can generate geometry, we focus on this question with some simple model. For instance, a model in which we add triangle through to each other through links, and every link is incident at most to k triangle. And so, for instance, we can do different move. For instance, we can add the triangle to a link, or we can kind of close this pi. And if you allow only at most 2 triangles to be an incident to a link, the network that is generated by this rule is this beautiful 2-dimensional manifold that you see here. So this is an example of emergent geometry, and this is for 2-dimensional simplicial complex, so only working with triangles, but you can do also in higher dimension. So you can have a tetrahedra and stick tetrahedra to triangular face. And this is actually generates, in general, in any dimension, emergent hyperbolic geometry if you stick a simplex to a face, so a triangle to a link or a tetrahedra to a triangle and so on. And this might lead also, if you add some feature of the node here represented as color and feature of the links and the triangle, this might lead also to topological transition in which you have growth only in one direction. So in the rules, there is no written that is in one direction, but you can have this breaking of this symmetry here. And we have also other model, maximum entropy model, such as the configuration model for simplicial complexes. And so if you are interested on the code, this is on GitHub. And yes, so this builds maximally random, so least biased simplicial complex with given distribution of generalized degree. So how many triangle each node is incident to, how many tetrahedra in a node is incident to, and so on. So these are beautiful models to play with when you define dynamics, because in absence of data, sometimes you just want to have a new model with a controlled topology on top of which you can study the dynamics. So let me just focus on the interaction between higher order network and dynamics, and we will focus mostly on this direction. So how topology shape dynamics. And topology is the study of shapes and shape invariant if you deform the shape. So for instance, a number of invariants are the Betti number. So the connected component of the network, or the cycle, the independent, the 2-dimensional cavity, such as the cavity inside the sphere, and so on. So it's clear that if you have, for instance, this fungi network here, you might want to represent the structure and indicate that there are important cycles in this structure. And so you might want to use topology to study this structure and this kind of relevance of this whole. And this is the kind of paradigm for topological tools such as persistent homology. But here we don't want to use topology to characterize the structure of a simplicial complex. We want to use topology to characterize dynamic. So as I mentioned before, in a simplicial complex, in a network, for instance, you can have dynamics not only defined on the nodes, but also on the links. And in a simplicial complex, you can define also on a triangle or in a tetrahedra, and so on. And so these dynamical signals associated to higher order simplices are, for instance, I think, for instance, an example to think about intuitively is the number of citations that a team gets, right? You have a team of 3 people that have a number of papers together. They get in this paper a number of citations that is associated to the team, not individually to an individual, but to the 3 co-authors. And or you can have a flux in biological transportation network, or synaptic signals between 2 neurons is associated to the link, or edge signals. Olaf Sporn is also defining edge signal on the brain. Or you can have current. So you can have vector defined at different location, such as currents or speed of wind. And these vector are defined at different location of the surface of the Earth. you can project into the triangulation of the surface of the Earth and treat a signal associated to the links of this triangulation. And so these are attracting increasing interest in signal processing and machine learning in general. But still, the problem of studying whether these topological signals can undergo collective phenomena is still less explored, and this is the topic of this talk. So let me just give a background in network topology. So in simplicial complexes are constituted by simplices. Simplices are a set of nodes. So a one simplex is a link, a two simplex is a triangle, a three simplex is a tetrahedra, and these simplices have an orientation. So here the arrow indicates the orientation. So the simplex, the link ij, has an opposite orientation of the link ji, and a triangle, as for instance, this triangle has a positive orientation in the anti-clockwise direction. So from these simplices, so these simplices are considered as the element of a vector space, and you can construct M-chains. M-chains are linear combination of the simplices of a given dimension. For instance, you can have these three links with some coefficient in front, and if you have 1, 3, it goes from 1 to 3, minus to 3, it goes from 3 to 2, and then 2, 4, it goes from 2 to 4. So you have a mapping between algebra and topology itself. So with this object, you can construct boundary operators. So operators that map each simplex to the simplices at the boundary. For instance, if you have a link, the boundary operator is the difference between the end node and the starting node. If you have a triangle, the boundary operator is built by the links at the boundary of the triangle with the right orientation. So with the orientation that is going here anti-clockwise, 1, 2, 2, 3, and minus 1, 3. So this boundary of the boundary is null. This is a topological constraint. So if you have a triangle, the boundary are the links around the triangle, but the boundary of that is 0, and you can work it out also. And you don't have to be afraid of this boundary operator. This boundary operator can just be represented as matrices that are rectangular, so formed by node and links, links and triangles. And here you have the boundary of the link 1, 2, which is 2 minus 1. And here you have the boundary of the link 1, 2, 3, which is 1, 1, 2, 2, 3, minus 1, 3. So you can work with these rectangular matrices, and you can do you can combine that and do some product. So if you have B1 transpose, this is another way to write the graph Laplacian, which you know is an important operator to define diffusion on a graph. But you can also, in higher order network, use the higher order boundary operator. And this higher order boundary operator defines diffusion from n simplices through n simplices, from n simplices to n simplices through n minus 1 or n plus 1 simplices. So you can go from link to link through node, or from link to link through triangle. And these two sectors are called Ln down and Ln up. And then they are defined in this way. And this higher order Laplacian, also called Hodge Laplacian, has important link to topology. For instance, its kernel has a dimension that is given by the Betti number. So its harmonic component can be considered as localized into the cavity of the simplicial complex. And moreover, these higher order Laplacian are such that they obey this Hodge decomposition. So for each signals, let's say on the links, you can decompose uniquely the signals on the links into a irrotational component going from a source, away from a source or toward a sink, or you can have an harmonic component going around the cavity, or you can have a curve flow, so a kind of a solenoidal component. So this is in the discrete realm what you can do in the continuous realm. And this Hodge Laplacian really describe very well the signals defined on one dimension. So for instance, only on links, you can treat it, the diffusion from links to links with the Hodge Laplacian, but they cannot be used to characterize signals, the interaction of signals living in different dimension. And what you need to do, to use for that, is the Dirac operator, in which you can, which can couple the signals of node and links and triangles and so on. So for instance, this Dirac operator, if you have node, links and triangles, is defined in terms of the boundary operator in this way. So it acts on the signals, on the direct sum of the signals of the node S0, signals of the links, and signals of the triangles. And it can couple the signals of different dimensions. So if you act the Dirac operator into the this topological spinner, you get on the node the divergence of the signals on the links, you get on the links the gradient of the signals on the nodes, and so on. So really, it allows crosstalk between signals of different dimension, and it's called the Dirac operator because it is to be considered the square root of the Laplacian. So if you do the square of the Dirac operator, you get this super Laplacian, which has the diagonal element, the graph Laplacian, the one Laplacian, the two Laplacian, and so on. You can go up to a higher dimension. The spectrum of this Dirac operator include, here defined on node, links, and triangles, include a sector defined on node and links. And you can have, so the right eigenvector of the boundary operator B1 and the left eigenvector of the boundary operator B1. And this is a eigenvector associated to a positive eigenvalue. But for each positive eigenvalue, you have also a negative eigenvalue, which has this set of eigenvector. So these are related by chirality. For links and triangles, you have the same. And then you have the harmonic component, which are instead only on nodes, only on links, and only on triangles in a suitable basis. So these are the topological spinors. And for instance, for a graph, you can have B1 transpose, where this B is a complex constant, the square is the Laplacian matrix, and you can really connect it with the Dirac operator, with the Dirac equation. So you can write a discrete Dirac equation for that, and you get that the eigenvalue are what you expect, where lambda square is the eigenvalue of the Dirac operator, plus m square, which m is this constant that you have put in this equation. And yes, and you can represent this eigenvector on any topology. For instance, these are the eigenvector on these fungi networks, and they are defined both on node and links. And this is another eigenvector or in another fungi network. And as I mentioned, there is this symmetry, kind of mass anti-mass symmetry, in the sense that for each non-positive eigenvalue, you have a single negative eigenvalue. which are related by chirality in absence of the mass. And for the eigenstate of the Dirac at the value of the mass, instead you don't have this symmetry. You have that the eigenstate at the eigenvalue equal to m are associated to the harmonic vector of the Dirac operator. And so they have a degeneracy that is given by the Betti numbers of your simplicial complex. So this is quite nice and interesting. So you can also push a little bit more the similitude with the Dirac operator, distinguishing between different directions. I want to give to be a little bit fast here. So what you can do is you can double the dimension on each node and on each links. And then instead of having this complex number B, you can have different Pauli matrices and using different rotation. If you go in the direction X, if you go in the direction Y, if you go in the direction Z. And yes, and the equation looks more similar to the three-dimensional continuous Dirac equation. And interesting, you can do this on lattices, these three-dimensional lattices, but you can also do this on multiplex networks where the links can have different type. So you can have a link present in 2 layers, a link present all in 1 layer or all in the other one. And also in this case, you have a relativistic dispersion relation, but the space is not anymore a tensor product. So you have that this Laplacian defined only on link 1, 0, 0, 1 or 1, 1 do not commute like in the cubic lattice. So this is interesting. And as you will see, we will use this Dirac to study also nonlinear dynamics. So let me first move and tell you how we use the Hodge Laplacian to study synchronization. So we will study synchronization in the framework of Kuramoto model on the network, in which you have traditionally a phase associated to each link and nearby phase connected by the network and nearby phase trying to align to each other. And in absence of the network, each phase has its own frequency drawn from a distribution that we take to be Gaussian. And then when the coupling constant is raised, we have a synchronization phenomena where a big fraction of the node oscillate together. So now our question is how to define an higher order Kuramoto model, coupling higher order dimensional topological signals. For instance, phases associated to the links, right? So this is work we have done with Ana Paula Millán and Joaquín Torres in 2020. And we are continuing to work on this model since. So our goal is to study topological signals. So for instance, signals on the links and their collective behavior. And so first thing we note that the Kuramoto model can be written in terms of this boundary operator in this way, where theta is the vector of the phase associated to the node, omega is the vector of the internal frequencies, and sigma is the coupling constant. And what we do is we consider now signals defined on the links. So for instance, on higher order simplicial complex. So for instance, if it's on the links, it's a flux, but it can be also on triangles. And we use both the boundary operator Bn and the boundary operator Bn plus 1 to define the same equation essentially. So now we have the phase associated with the link, the intrinsic frequency associated with the links, and links are coupled to each other if they share a triangle or if they share a link, for instance. And the linearized dynamics is we get the Hodge Laplacian instead of having the Laplacian. And from this, we see that the harmonic mode remains freely, they oscillate freely. These harmonic nodes are, of course, localized into the cavity of the simplicial complex. The one-dimensional cavity if it's a link, a two-dimensional cavity if it's a triangle dynamics. And the other mode frees asymptotically in time, and they obey these relaxation dynamics. So this is the linearized dynamics. In the nonlinear dynamics of this topological Kuramoto model, always we have that the motion, the dynamics is localized on the harmonic mode. And the other modes are slowly, eventually freezing, and they can be monitoring by projecting the dynamics defined, for instance, on the links. You can project it on the triangle or on the node. And in order to project that, you can use the boundary operator, which can, as an interpretation, for instance, the discrete curl of the signals of the links, or the discrete divergence of the signals of the links. So the discrete divergence is defined on the node, the curl is defined on the triangle. And from that, you have these two projected dynamics, which are screening out the harmonic mode. So the harmonic mode oscillate freely, and the other mode are captured by these two projected dynamics. And this one undergo synchronization. So they have an order parameter that show that they freeze. So the only mode that they are dynamically moving are the one around the cavities. And these occur at zero coupling. And you need to do this on node and links separately. And only like this you can detect this synchronization. So you really need to use topology to detect synchronization. What we have done, we have now coupled these two projected dynamics in using an order parameter on modulating the interaction between, let's say, link sharing a triangle with the order parameter of the projected dynamics on the nodes, and vice versa, the coupling of node sharing a link is modulated by the order parameter of the dynamics projected on triangles. And now the two projected dynamics are not anymore decoupled. They are coupled via this order parameter, R plus and R minus, and this is responsible for the emergence of explosive synchronization. So this synchronization becomes discontinuous. This is on the configuration model of simplicial complex. We have done simulation also on real network, for instance, on the Homo sapiens connectome and C. elegans connectome, finding similar result. And we also look at this network geometry with flavor model, finding similar result. So we have done several work to extend this in different directions. One work is to have signals now defined both of node and links. And the first thing that we have done is always to have this global coupling of the dynamics. So we modulate the dynamics of the Kuramoto model here by this order parameter of the links projected on the nodes. And so we modulate with this global order parameter. And in this way, we find that the synchronization occurs simultaneously on node, on links projected on nodes, and links projected on triangles in a number of cases. And for the random graph, for Poisson graph and power law graph, we have a theory which really captures very well the backward transition. The forward transition is not coupled by the dynamics because in this model, it is a finite size effect. So it goes to infinity in the thermodynamic limit. However, until now, we have discussed how to couple these projected dynamics of nodes and links in order to have a synchronization of the transition. But this explosive synchronization transition, but to some extent, this is not completely satisfactory because the coupling was global, right? So if you have a real system, in many cases, you want to couple dynamics of node and links, you might want to have a mechanism that couples nodes to nearby links and links to nearby nodes, and not having a modulation by the global order parameter. And this can be achieved using the Dirac operator. So first of all, you consider that the dynamics of the Kuramoto model and one of the links, but when you neglect triangle, where there are no triangle, it becomes this equation. These two equations can be captured by single equation, which can be written in terms of the Dirac operator, which reads like that. But really, this equation is the same as these two. So node only are affected by node, and links are only affected by links. So we want to use the Dirac operator to make node and links interacting. So what we did is we introduced a phase lag in the dynamics, depending on higher order power of the Dirac operator. There are some subtlety of this model. So we use the normalized Dirac operator. This seems to be to work to be a good choice. So we normalize essentially by the degree of the node. And we have this gamma matrix, which is the gamma of the chiral symmetry. And so, and I will comment on the necessity of this gamma matrix, and Z is a parameter. So now the dynamics on the node has a phase lag that depends on the dynamics of nearby links, and the dynamics of the links has a phase lag that depends on the dynamics of nearby nodes. So node and link signals are entangled, and actually also the order parameter depend on linear combination of node and links. And if you look at the linearized dynamics, is instructive because the harmonic component are always the kind of where the dynamics lies and is unchanged by the coupling. And then you have this non-harmonic mode, which are coupled together in this way. And this mode, they freeze, but they freeze instead of having a fixed point, they have a stable focus. So these dynamics start to induce also in the linearized version a kind of intrinsic frequency of the system. And so here the comment is that this gamma allows us for this matrix to have always a real negative part, while if we add an identity here, we might not allow all the value of Z. We might only allow a certain range of Z. So this gamma matrix allows this to have Z arbitrarily big and still have a linearized dynamics that has a stable focus. So this is the phase diagram for this Dirac synchronization as a function of Z. So you can have a discontinuous forward transition and a continuous backward transition, but as Z is increased, also the backward transition become discontinuous, a little bit like it happened also for the Sakamochi-Kuramoto model. And what is very interesting is that this complex order parameter now acquire an intrinsic frequency also in the rotating frame of the intrinsic frequency. So they have an emergent frequency also in the frame of the intrinsic frequency. So we put the intrinsic frequency to 0 and still we get this oscillation of this order parameter X alpha, which is quite clear and with absolute value constant. And then as we lower sigma, so we go toward the backward synchronization transition, there are these other frequency that's set in. And so we believe that this can be interesting to understand the topological effects that generate spontaneous emergence of low frequency rhythms. Okay, so this concludes in some sense our work that is ongoing still on collective dynamics of topological signals. And I want now to conclude the talk speaking about this direction. I said this direction is being explored in the network science, but here I want to show how combinatorial and statistical properties shape network dynamics, and there will be still some topology and still some nonlinear dynamics here. And this is a very exciting work we have been doing with my student Lin Sun and Jürgen Kurz and Filippo Radicchi. Has been a beautiful collaboration. So our object here is another type of higher order networks, the one with triadic interaction. So an triadic interaction is when one node affects the interaction between other two nodes. And this can be positive or negative. So for instance, the presence of a species can enhance or inhibit the interaction between other two species, or the presence of a glia can change the synaptic interaction between neurons in a positive or negative way. So these triadic interactions are popular in neuroscience, are popular in ecology, but they are not very familiar with statistical mechanics people or people working on nonlinear dynamics. And here we look at the global effect of this triadic sign interaction in network model. So in particular, a special focus will be the fact that these triadic interactions are signed. And as we see, as we know, sign interaction can dramatically change the phase diagram of models. For instance, the easy model can become a spin glass, which is very different phenomenology. And here we show that with triadic interaction, percolation changes nature and becomes a fully fledged dynamical process. So percolation is the study of what happens if you have a network and you damage the links with probability 1 minus p, and then you monitor the giant component, the fraction of node in the giant component. And as p is lowered, the giant component is lowered, and at the percolation threshold becomes 0 if you start from an infinite network. So this is the scenario in a random graph, and this giant component R is captured by these two equations. So now we want to study percolation in presence of triadic interaction. So our network will be a network of nodes and links. So the nodes are this blue blob, and the links are this solid line, also represented as this diamond, indicating the links. And then some of these nodes regulate the links, so have the ability to switch off or switch on the link. And so the red is negative regulation, the green is positive regulation. So what we assume is that regulatory interaction determine which links are active. So structural links are active if they are connected to at least one active positive regulator node, and they are not connected to any active negative regulator node. And structural interaction determine which nodes are active. So the nodes are active if they are in the giant component of the network. So we consider an algorithm. So we start with a network and given probability that the nodes are on or off, and we evaluate the giant component. The node in the giant component are the ones that are active. Then in step 2, we regulate the links according to this activity of the node. So we deactivate all the links that are connected to at least one active negative regulator node, or they are not connected to any active positive regulator node. And then we introduce also some stochasticity. So all the other links, all the links that are possibly on, they are damaged or regulated down with the probability 1 minus p, such as occur in percolation. So there is some stochasticity, but also some deterministic rule of deactivation. And then we start from step 1. So this is a toy model. So in this toy model, all the nodes are active, all the links are active. But then since this node is active, for instance, this link is damaged. And these two links are damaged at this iteration. So these two nodes are not in the giant component, because if these two links are damaged, these two nodes are not connected to the rest. But if this node is damaged, then this link is damaged at the next time, and so on. So you see here, there is this interesting fact that we see that at time 2, we get the same configuration that we get at time 4. So there is blinking. So the network goes on and off in time. And this is captured by our theory, which includes the equation for percolation and the equation for regulation of the link. So R is the fraction of the node in the giant component, depends on the probability that the links is intact, and the probability that the links is intact depends on the probability that the nodes are active. And so we have a cobweb plot describing these dynamics, and from this cobweb plot, you can see that there is a period 2, and this is confirmed by our simulation. So we can see a giant component of a fraction of nodes that oscillate between 90% and 50%, so going up and down. And so this is a movie of what can happen. So the network is switching on and off with period 2, and this can go forever. But if you change the parameter, you can also have period doubling, and you can also have chaos. So this is a time series of the giant component. So the fraction of nodes, this is the time series of the fraction of nodes that are connected in time. And this is a corresponding movie. So you can have a connectivity that change in time. So connectivity now becomes a dynamical notion that can change in time in a chaotic way. And so this is really, as far as we know, the first time in which percolation has been considered in this nonlinear dynamic way. So in absence of triadic interaction, you can have this phase transition from giant component, which is almost 1, you lower P, and the giant component decrease, and this is a second order phase transition, very much studied in the literature. And here, in this case, you have, in presence of triadic interaction with also negative regulation, you have that your phase diagram becomes an orbit diagram. So you can have 4 possible giant components, a chaotic region, and then 2 giant components, just 1 component, and then 0. And these are the theoretical prediction with this mean field equation, just 3 equations. And these are the Monte Carlo simulation for this process that is, of course, stochastic and has a lot of degree of freedom, because every link is a different degree of freedom of the system. So it's impressive how good the theory is with the Monte Carlo simulation. This is 10,000 nodes. So we did this. So while the theory works only on random graph, which are Poisson or scale free and so on, we also can run the algorithm on a real dataset, network dataset. We took a mouse brain network. We put there some random regulatory interaction, and we see that there is this possibility of having this kind of blinking of 2 different sorts of giant component for this space, or here something more a continuous of possible fraction of node in the giant component, so more a chaotic region here. Finally, in absence of negative regulation, we see that this time dependence of the size of the giant components disappear. So you always reach a steady state, but the dynamics still remain quite interesting because this triadic interaction made percolation discontinuous. So this is a discontinuous hybrid transition, and we have a theory for that is very well in agreement with the simulation result. But really here the lesson is that in order to see this non-trivial effect, you really need negative triadic interaction as well. So I reached my conclusion. So higher order interaction are ubiquitous in complex system, and they are characterizing the combinatorial, topological, and geometrical property of higher order networks. And higher order dynamics really displays unexpected phenomena, including higher order synchronization and this percolation regulated by triadic interaction. And the Dirac operator is, without any doubt, a very important operator to treat the dynamics of topological signals of different dimension. And so thank you so much for your attention, and we have for the questions.
Thank you very much for this very nice talk. I request the audience, they can type the questions into Q&A box so that we can keep things in order. So please feel free to ask anything in the Q&A box. Yeah. Yes, Gaurav, you can, let's see if I can turn this thing on. Yeah, Gaurav, you can ask. Hello, go ahead, please. I should turn.
I feel it's quite. Can I read this question now?
Yeah.
I feel it is quite easy to intuitively understand pairwise link than tetrahedra in higher order network. What is your opinion on addressing this point? Yeah, well, higher order network are quite intuitive. So for instance, think of a collaboration network. Collaboration network is about teams of people. So I think this gives a good intuition of why you need higher order networks. You also have you know, social interaction, like group interaction between people, face-to-face interaction between people is not only occurring in pairwise interaction. Protein interaction networks are building complexes with more than 2 protein. So you in order for the protein complex to build some function, you need more than 2 protein. These topological signals, yes, I mean, but you have signals on the links very often. Any flux, any transport network, you have a flux on the links. So in order to treat flux on the links is quite useful to use this Auger Laplacian. Yeah, so I think it's just you need to train yourself, but after you train yourself, you see this occurring quite widely in a number of applications. Thank you.
Shruti Tandon, you have a question? You can. Yeah, go ahead.
Yes, I have a question. So it was a great talk, Professor Bianconi. Thanks for the talk. So you discussed how the structure of the simplicial complexes or the network that affects the dynamics of the system, right? But say we have a system which exhibits spatiotemporal dynamics. So can we encode the dynamics into the structure, and by studying the structure of the network using these higher order networks, how can we analyze the dynamics?
Yes. So so what is clear from this higher order synchronization is that the collective phenomena is on the cavities, right? Usually you think of synchronization something that, if it's global synchronization, all the nodes oscillate on the connected component at the same time. Here instead, they are localized on these loops and cavity. So this makes a very rich relation with topology, because topology is about this cavity and these loops. So how it's important. And this is a way to show that they are important for dynamics. We have actually also other work, previous work on network geometry. So in the case of this topological synchronization, we have not explored many particular network topology. So we've done a random graph, fully connected network, or something that is not very structured or doesn't have a lot of community. But our preliminary results show that if you have some network with community, for instance, this topological synchronization is very particular. So you have spatiotemporal effect. What we have done in terms of publication, we have published some work on the simple Kuramoto model on network geometry. So simplicial complex built by this network geometry with flavor. And so we have a paper with that with Ana Millán and Joaquin Torres. And we have shown that actually, yes, there is spatiotemporal synchronization. So you might have system in which the synchronization is not reached thermodynamically, so you have only phase entrainment, and then you can have also so you have the order parameter that oscillate in time very strangely, and you have also that the community or switch on and off, so that you can have a order parameter localized on each community, and this order parameter localized on each community, they do very different things. So this is how we characterize spatiotemporal effect in simplicial complex. And you can have a lot of that because simplicial complex can have a non-trivial geometry. So in particular, also community structure and spectral property.
Okay, thank you. I have another one small question. It's more like asking for a starting point. So you discussed about algebraic topology, that has this huge applications in visual complexes. So what would be a starting point for engineers?
For
engineers, I mean.
Okay, my book.
Oh, okay.
Easy question.
Okay.
Thank
Great.
you.
Yeah, I just bought your book. So just started to read it. And there's another question from Dr. Kohler in the chat box. Can you?
Yes, very nice presentation. Did you observe any instability? Do you also have damping of the dynamical behavior? And if so, how would that influence the mitigation of the instability of the evolution of new formation of when we observe the hysteresis loop for the Dirac synchronization, here this as I mentioned here, in this work, the forward transition is a finite size effect when there is a global coupling of the order parameter. But in this Dirac synchronization, no, this forward transition define a stable hysteresis loop, and And this is driven by the instability of the unstable solution. So that here becomes unstable and it's like going in the coherent phase. So yeah, I don't understand very in detail your question. Yes, but in this case, there is this instability of the zero solution. And for the moment here, maybe you are referring to the percolation, to the percolation model. Yes, you are right thinking of it. I didn't mention this. So this is, you have this phase diagram here, in which you have practically root to chaos and back as a function of P. And this, however, this phase diagram depends a little bit on the initial condition, in the sense that if for other initial condition, instead of having, for instance, this first part of the phase diagram, you might have 0. So there is a basing of attraction for this attractor and a basing of attraction for the zero solution. And depending on the phase diagram, the zero solution can be still stable also, like in this region here. So maybe if you start with some not good initial condition, you just see 0, 0, 0, and then just chaos instantaneously. So it depends. This phase diagram depends on the initial condition. So there is this, is either this, the attractor, or the incoherent zero phase. I don't know if this was your question. So
Yeah, thank you. If anybody else has questions, please feel free to type it. I have go ahead, Praveen.
Yeah, Professor Bianconi, thanks for the nice talk. And I have a question on for when you are constructing higher order networks, what is the, how will you reason to choose, say, a triad or a tetrahedron, or what is the basis of choosing such a link? For the case of a collaboration network involving 3 co-authors, I understand that it makes sense to choose a triad. But then say we have a spatially distributed spatiotemporal system, such as an engineering system or a natural system, how will you choose the number of links to consider, and what types of the whether to choose a triad or a tetrahedron or anything further than that, or yeah.
So yeah. So yeah, so there are different questions, right? One is how to model.
Yes.
And one is how to do inference. Okay, so if you want to do inference, I think you need to, the most powerful way would be to be most general and say you want simplices of any order potentially. Maybe you want to put a upper cutoff. I mean, you want to say, I don't consider simplices or hyper edge of more than 10 nodes, right? Because it would be computational demanding, for instance. And then you want to say, to have an inference technique that tells you if there is a interaction of 8 or 6 or 5 nodes. In terms of modeling, you can model both simplicial complex and hypergraph. So the model that I discussed are pure simplicial complex, which can be considered also as hypergraph of with hyperedge of a given cardinality. So you work only with triangle, only with tetrahedra, only like that. But we show in a paper that this is not a limitation, because practically you can stack them one on top of each other. So you can have a network, right? Node and links. And then the same number of nodes here in another layer, which are only interacting via triangle.
Okay.
And then here you have another set of the same set of node all interacting with tetrahedra. And then you consider the aggregate of that. That would be a suitable model for a hypergraph, which has up to 10, let's say,
as long as the
edge or up to 10 degrees. So you can stack this model on top of each other. So for instance, in our code, we have to build a graph, to build with triangle, to build with tetrahedra, but you can use it together, right?
yes.
You can use it one together with the other one, and then you will have a structure that is a hypergraph, so that you have tetrahedra, triangle, and links, but you might not have all the links in the triangle, or you might choose not to have. So to have a triangle without having the 3 links around the triangle.
Okay.
This will be an hypergraph.
Yeah, thank you. I think that makes sense. And I have a follow-up question. In one of your slides where you show the examples of higher order networks, there was, I think, a wind transport was one of the examples. Can you explain that? Where you show the citation, collaboration.
Biological transportation network, right? So if you have sorry,
I think in the beginning.
Yeah. So you can have
yes, speed of
traffic, right? Flux of biological transportation network, for instance.
I want to
I don't know, blood, right? Blood vessel, or in a leaf you can have flux of in the leaf structure of, or you can have also synaptic signals between neurons. You have a signals between them, right? Or you can also have road traffic, right? So in a road you have a flux, and this is associated to the links, right? And if you say this direction is positive, you will have a flux in this direction, with positive in this orientation, and in this other orientation. So you have
you can design the links based on that.
In general, every function defined on links, and these have been taken into account in the literature, but not so much, and in particular, not this collective dynamics. And what we show is that you can have these dynamics on node and links that are also interacting with each other, so that you can have some crosstalk between these two signals.
And finally, is there any package like Network X for higher order networks?
Yes, there is. I don't remember a lot very well the name. I think probably Leo Torres and Landry. They have it. I don't remember the name. So there are certainly a lot of package for topology, but for higher order network, I think there is this new one in Python but yeah, I still haven't used it. We are working with online on homemade code, but I think it's good, so I plan to use it, but I don't remember the name now. So I think Leo Torres and Landry. I don't remember his first name now. Should be the author.
Yeah. Thank you. We'll find it out.
There is a question in the Q&A box, actually. Can you just see?
Q&A.
Fairly long.
Let me see. Yes. So I have a question regarding the interplay between multiple subunits. For example, the interplay between subunits such as different brain area can lead to the emergence of rhythm in the gamma frequency band. I mean, the interplay between subunits plays a major role in deciding the dynamical state of the system. So what is your opinion on how much a higher order interaction model can provide insight in the case of a multiple subunit interaction system? And then there is another question. Can you explain the reason for adding order parameter in the equation of Kuramoto model to get explosive synchronization? Okay, let me start with the first. Yeah, so this is quite interesting. You have different level in terms of subunit, as you call it, and whether higher order network can in some sense include that or take into account that. In general, higher order network are endowed with this structure with node links triangle, this kind of hierarchy in terms of dimension at which of the interaction at which you look at. But yes, so for instance, in this hyperbolic network here that we have built, here there is also a notion of kind of subunit, because it's so it can, this is a manifold, but it might also not be a manifold, and then you can have a generation of community that generate and split. And so the fact that you work with a building block like a triangle might lead to a mesoscale structure that is a community. But yes, in terms of dynamics, yeah, so it is an interesting question, but we have looked at this only for the emergence of community. And the other question, so it's a beautiful research question. I think it's quite worth investigating. And the other question is, can you explain the reason for adding an order parameter in equation of the Kuramoto model to get explosive synchronization? So this is not such particularly original thing that we have done. So this has been done in other contexts also by the group of Stefano Boccaletti. What is interesting is that actually this is a mechanism to get explosive synchronization, but it's not the only one. Actually, with the direct synchronization, we don't have global order parameter. So this is with the with the global order parameter, and we get explosive. But also with the Dirac, that doesn't have this mechanism. It's purely topological. And then we get explosive synchronization of both the forward and the backward transition. So I think, yes, we were looking for ways to get this explosive transition. So first we explore this kind of method that is already in the literature, that is modulating with a global order parameter. But then we did more, because actually this model here doesn't have a modulation with the global order parameter. It's only the Dirac operator that acts, and this can generate this explosive synchronization. So we believe this is actually a good result.
Okay, great. I think you have answered all the questions that are there. So I just want to thank you once again for this very interesting talk, and this generated a lot of interest. And the next seminar will be on November 28th by Professor Rajesh Roy on complex photonic dynamics, counting single photons, birthing chaotic attractors, and generating random numbers. Once again, thanks everybody.
Thank you so much.
Bye.